That's interesting. Is that better? Hang on, this works. Okay, can you hear me now? All right, I won't touch this control thing again. All right, so last time, oh, it's loud now, is it? It's good? Is it okay? Is it too loud? It's good, all right. It just sounds loud to me. All right, review of last time, we looked at the generic search algorithm, and last time we looked at the case of depth-first search, where the frontier is a stack, breadth-first search, where the frontier is a queue, or lowest cost first search, where the frontier is a priority queue ordered by the cost of paths. Okay, are there any questions about that? So that's what we did last time. And we ended up doing this complexity analysis. And so here is what people were asking questions about on Piazza and other questions I've had. So if n is the path length to the closest goal, and m is the maximum path length in a graph, which in this case could be infinite, and b is the branching factor, which is the maximum number of neighbors. So which parameters does the complexity of breadth-first search depend on? What does it depend on? The worst case complexity. What does it actually depend on? Which of those three numbers does it depend on? M, right, depends on M. Oh, depends on M. What else? B. Okay. The worst case complexity doesn't depend on the number of path length to the closest goal, because basically it searches this big graph until it sort of stumbles across this. Right? What's the time complexity? What's the time complexity? Right, it's b to the m. And what's the space complexity? So we did last time. Do you remember? It's b times m. All right, so essentially the path length, the longest path length is what depends on this. This is why we effectively said in the worst case it's infinite, because the maximum path length can be infinite on graphs with cycles. But the space complexity is linear. So what about breadth first and lowest cost first search? What do they depend on? Yeah. Right, it depends on n, the path length to the closest goal, and b is the branching factor. Okay, so if a big graph, it doesn't matter about these very long paths because we're not going to get to them. And in here, the complexity of all of these is exponential in b to the n for all of these. Okay, it's exponential. You essentially have to search this whole space of up to the length of the shortest path. Lowest cost first, it depends on the cost, whereas the breadth first search depends on the number of steps. Yes?
Usually, conventionally, when we discuss time complexity, we usually refer to the number of nodes, number of edges in our calculations. I was wondering if you could elaborate the advantage of using path length and the branching factor as opposed to just the number of nodes.
Because a lot of the problems we have infinitely many nodes, are unbounded graphs, and it doesn't actually depend on, for example, the breadth first and lowest cost doesn't actually depend on the number of nodes. It only depends on the path length of this other node. And basically because the formula is reduced to these three numbers most easily. Right, so it's the number of arcs, so it's how far you have branching. Because some of the graphs we'll find are very simple to compute. So if we have a tree, right, and we search down here, the branching factor might be 2. But if I go backwards, if I think of the inverse graph of this, the branching factor is only 1. And in fact, all these graphs, it's very quick to find a path from a start node to a goal going backwards than it is to go forwards. So the complexity in these graphs depends on the actual branching factor, not merely the number of nodes and arcs. Okay? Yes?
The maximum number of the paths available are the same as path length to the closest point?
Sorry, so if we have a graph that looks like, and there's a goal here, and there might be other, right, this one here, n is this distance, so n here is this distance, and m is this distance.
So the number of paths does not have anything to do with time and space complexity?
Here we're just doing the path length. Well, the number of paths is exponential, so b to the n represents the number of paths. So the number of paths is of order b to the m. Any other questions? Yes?
The lowest cost first search essentially the same as the Dijkstra algorithm?
Yes, except when we do least cost first plus what we call multiple path pruning, it's equivalent to Dijkstra's algorithm. So we're going to do something else. So this one here doesn't, if we have multiple paths to the same node, it doesn't prune them off. And we'll do that later. And then that's equivalent to Dijkstra's algorithm. So Dijkstra's algorithm is equivalent to lowest cost first plus multiple path pruning. We'll get to it. We'll do it soon, but we're trying to... All right, any questions about that? Okay. All right, so let's do a clicker question. So here's a particular graph. And we're going to start node is going to be Z, and the goal node is Y. And we're going to assume, like we did before, is the children are expanded from the left to the right. Let's move this over here. Does everyone understand the question? Okay. Any questions? Let's start this. Right, so start node Z, goal node is Y, and we're going to know whether breadth first and depth first and least cost first all halt, whether none of them halt, whether depth first and least cost first halt, but breadth first search doesn't halt, or whether breadth first and least cost first searches halt, but depth first search doesn't halt, or none of the above. All right. All right. "57% got the right answers, D. All right, let's go. Unfortunately, my computer crashed when I moved into here, so I'll just open a file here. Load sample problem. Whoops. Cancel, it's not a sample problem. Sorry. Load from file. Where am I? Whoops. World / AI book / code / all right. Hopefully this is the same graph. View, font size, large, and all. And let's do a search algorithm, depth first search. So what happens in depth first search here? So if I'm going to step, whoops, I have to select start node. Sorry. And what was the goal node here? Y, is that right? Whoops, goal node. All right, so if I do depth first, so what do people say? So often people said, let's do all of them. So I'm going to, so this is depth first search. I'm going to step. What am I going to choose first? Next. P. Then what am I going to choose? Q. Then R. Then P. Then Q. Then R. And it goes on. Okay? Questions? If I do breadth first search, if I do breadth first search, I'm going to reset it. I'm going to step. What do I expand? Then what? Then what? Then Y. Okay. Everyone happy with the answer? Questions? Yes. Mm-hmm. Yeah, we will in a minute. We'll do that. We're going to do that, but that just adds more complexity. Let's understand this algorithm first. Yes?
Is there possibly also a way to modify the depth first search algorithm so that we can detect where the mistake could happen?
Sorry, what?
Is there a way to modify the depth first search algorithm for it to detect if it is running into a loop?
Yes, we're going to have algorithms that detect when it's running through a loop. We're also going to have algorithms to detect multiple paths to a node, but they have different complexities depending on the search methods we're using. So we'll look at that later. Any other questions about that quiz question? All right. Let's do the next quiz question. All right, looks exactly the same, but here it's the start node is Z and the goal is W. Let's start this now. So it's exactly the same question as before, except the start node is Z and the goal is W. And what happens? All right. Let's see what everyone says. We ain't got 52%. In fact, the answer is B. Let's do it again. Let's reset this search. The goal is now... I know how to create this. That's set as a regular node. W is the goal, right? Now we're going to go to solve mode here and we're going to step. So this is depth first search. Oh, it doesn't care about the goal. It didn't happen to stumble on. It's exactly the same as before. So depth first search doesn't halt, right? Same as before. Okay, what about breadth first search? What does it do? Well, it's going to go, breadth first search. It's going to go PS, and it's going to keep wandering around, and eventually it ends up on searched all the paths of length 1, now it's searching paths of length. Quite long paths, but it's still going around this loop, right? So it doesn't halt either. Remember, the complexity before was to a solution, but there is no solution to this thing. There's no path from a start to a goal. Right? So when we did the complexity, it was the path to a solution. But here it's actually just going to search the whole space because it can't find a solution. Okay? Any questions about that? Okay. Let's do one more question. Same graph. Now the start node is W and the goal is X. And it's the same question as before, same choices. How am I going? We're getting more people, that's exciting. All right. Oh no. At least the mode is correct. Let's do it again. So what was the question? Reset the search. Hang on, what was this? Regular node. So W is the start node, right? Oh, I hope it's not also a goal node. And X was the goal node, right? Hang on, what's W now? Okay. And we're going to go to depth first search. Okay, let's see what happens. We start with W, we go to S, then T, what gets expanded? Depth first search. S, what gets expanded? What gets expanded? What gets expanded? No, there are no paths on the frontier. We've stopped. Oh. And we stop. Makes sense. We start off with W, we went to W and S, WSY, WSYT, then the WT path, and then there's no more paths. Does that make sense? Questions about that? What happens in breadth first search? We might as well do it just for completeness. And if we're going to step, we're going to do S, T, S, T, the path to Y, the other path to T, and there are no more paths. So we stop again. Does that make sense? There are no solutions here, but we didn't reach the worst case. We went through a loop. It was just a nice, small, finite part of the graph we searched. All right, questions? All right, we'll do one more question. Here's one from the. Here's one more question from the. Here's one more question from Piazza. Will the lowest cost work in cyclic graphs? Well, we have to define what works means. So let's make it precise here. Will lowest cost first search halt and find the least cost solution if there is a solution in cyclic graphs? Right, so will it, if there is a solution, it'll find one. And what's the answer? 3. Ah. Well, that's interesting. Why is the answer no or maybe? Yeah. Hmm? Negative cycles in a graph. What's a negative cycle?
Well, like for example, if the cost is like one edge is negative and then negative and it's a cycle, then like as you go around the cycle gets more and more negative, so then the cost is.
Ah. Yeah, we actually defined costs earlier as being non-negative, but no one will remember that, will they? Yeah.
The algorithm has no way to detect that it's in a cycle, so it could conceivably get stuck in a loop.
But doesn't care.
But if it's in the loop, it's not going to get to the solution.
Yes, it will. Yes, it can. Well, let's do a graph where it does. So if you have a cycle, if you have a graph like this, as a cycle, and then there's a path down here, even though it gets in the cycle, it eventually is going to choose this, then this, then this, then this, then back to here, then this, then back to here, then this. So it's going to eventually go around this loop. As long as all these things are positive, they're not 0 or negative, it's going to eventually find this goal, even though it's in a loop. Yeah. What? Well, it assumes there is a solution. So there is a, it assumes there is a solution. Yeah. Yeah, but there was no solution. That's why I defined the question said if there is a solution. The solution is there is a path to the goal. Yeah. Hmm?
What about acyclic graph without cycles?
Without cycles,
Yeah, we have that graph.
is it finite or infinite? Potentially infinite.
Is it guaranteed to find a solution with the lowest cost part?
So if the graph is acyclic and is finite or potentially infinite? Finite, then yeah, everything will halt. All the algorithms we've seen will halt in that case. So if it's acyclic and finite, there's only a finite number of paths from a start node, and they'll all just get explored. So, hmm? Is there a goal node here?
C is the goal.
C is the goal?
Oh, sorry, D, sorry. D.
Okay.
Yeah. And A is the start node.
Yep.
A to C is cost is 2. And then B to D is 3. And then C to D is 1.
Yep.
So which path it will find? It goes from A to B.
If we do this, the frontier starts off as A, then it has AB and BC, right? Then it's going to select this one, which is going to select this one. Oh, sorry. Thank you. AC. Then it's going to add this to the front. Then it's going to collect. Then it's going to have what? ABD. ABD. What's the length of this? 4. And there's also ACs on the front here. What's the cost of this? 2. So what's it going to select? AC, right? So it's going to select this one. Then it's going to have AC. What is its neighbours? ACD. So then it can have It's going to have the frontier is going to be ABD of length 4 and ACD of length 3. What's it going to select? It's going to select this one. The algorithm it only checks for whether something is a goal when it's reached the node. Okay, other questions? Okay. Other questions? All right. All right, let's go. So we've done so far as these methods here, the depth first, breadth first, and lowest cost first search methods. And complete means it's guaranteed to find a solution if there is one. Halts is whether it halts on a finite graph, perhaps with cycles. And the space is a function of the length of the current path we're talking about. So all the paths we're talking about, current paths, the space of depth first search is linear in the number of paths. Depth first search is not complete. It's not guaranteed to find a path. And none of them are guaranteed to halt because they can all get stuck in cycles. Okay, does that make sense? Okay. All right, so let's start what we're going to do today. That was a review of last class, but that's fine. So at the end of the class, we should be able to devise a useful heuristic, talk about heuristic search now, devise a heuristic function for the problem, demonstrate how best first search and A* search will work on a graph, and predict the space and time requirements for best first and A* search. All right. So the idea is all the algorithms we've seen so far have effectively ignored the goal until we've stumbled upon it. So they all just wander around and just keep searching through this space until they find a goal and they say, we found it. But they ignore the goal when they're searching. So what we're going to do is look at extra knowledge that can be used to guide the search, and we're going to call these heuristics. And in particular, we're going to look at one heuristic, which is h of n, is going to be an estimate of the cost of the shortest path from node n to a goal node. And what we're going to assume is that h of n is something that's quick to compute. And so we're going to then use this h of n, this heuristic, this extra knowledge about an estimate of how close we are to a goal in order to improve our search. So we're going to use estimates of something extra we know about this domain, and it's not just an abstract graph that has no meaning to it, but actually has meaning to it. We might know, for example, that it's a map of, in Google Maps, they actually know a lot about the graph than it's just the nodes and arcs. Then we're going to extend h to paths. So we're going to talk about h of a path, and it's just h of the end of the node. So the h of paths is just the heuristic value of the end of this path. And h of n is an underestimate if there's a path from n to a goal with cost less than h of n. So h of n is an underestimate if the actual cost is greater than or equal to that h of n. And an admissible heuristic is a non-negative heuristic function that's an underestimate of the actual cost from a path to a goal. So a non-negative number that's an underestimate is what we're going to call admissible heuristic. Okay. So if h of n estimates it, then it's less than the actual cost. Less than or equal to the actual cost. All right. So people have, so let's look at some of these. If the nodes are points on a Euclidean plane and the cost is the distance, what can h of n be? We have a graph like we did before, like this Google Maps graph. Oh, I lost it, didn't I? Oh. I had these all set up on my computer, but then my computer crashed. Okay, let's do it. If you have a Google Maps and you have distances there, and you're optimizing distances, the cost is the distance. What's an underestimate of the cost of a node? Well, but we have this graph, like a graph of Vancouver. What's Vancouver look like? And there are arcs in here, and there are roads, and you have to do here. And I want to know from UBC, the start node here, and the goal node here. We don't know the distance, so it can't be half the distance. Yeah. Yeah, so it could be the straight line distance as one underestimate. So this one here will do just this straight line distance. Yeah. Yeah, we could do Manhattan distance, except Vancouver roads aren't as nice as that. It's not really an underestimate when we don't get... It has to be an underestimate, right? It has to underestimate what we're doing. Yeah.
Consider it to be constant?
Hmm?
Do you use a constant?
What constant can I use?
1.
I can't use 1 because it doesn't work for G. It's not an underestimate for nodes close to G. It's not an underestimate. I can't use 1 because I can't use 1 for every node because it doesn't work for G. What could I use?
The only constant you can use would be 0.
Yeah, the only one I can use is 0. I can use 0. So h of n is 0. We often call this the trivial heuristic. And this is what we're going to do. This is the search algorithms we're going to look at with h of n as 0. We're going to be like the other search algorithms. Yes? Yes. Less than or equal to. And in fact, equal to is what we'd like it to find. We'd like to get something that's, if we can find one that's equal, then we can just walk straight to a goal. Yes?
Why does it need to be an underestimate?
Well, we'll talk about that in a minute. At the moment, it's just a definition. We'll talk about why it needs to be underestimate. But in the answer, it's going to be because then we can make guarantees about what's going to happen. All right, the straight line distance. What if the cost is time? What can we do?
Straight line distance divided by the speed of light. It's true.
Well, the straight line distance is decided by the maximum speed that people can travel, you know. Google Maps doesn't give you a time estimate for, right? The distance divided by the maximum speed. Okay? If the goal is to collect all of our coins and not run out of the fuel, right, h of n is h of n is an estimate of how many steps it will take to collect the rest of the coins and refuel and return to the goal position. Right, we're just trying to guess how much this takes. So it's just a guess. We're trying to estimate this, and we could have all sorts of different estimates of this. We could ignore the coins. We could ignore walls. By ignoring parts of the problem, we can get this heuristic function. So we could ignore coins. That would give us just the distance would give us an underestimate. We could ignore walls because walls increase our distance. We could ignore fueling because refueling increases our distance we have to travel. Okay, so there's a whole lot of things we could get an underestimate in order to use this. And typically what we're going to do is we're going to found by solving a simpler, less constrained version of this problem. Typically we're going to solve some simpler problem. Just suppose you can go directly. Just suppose you could ignore the coins. I suppose you could just travel at arbitrarily speed, ignore traffic. Okay. All right. How am I going? All right, so the first one we're going to do is best first search. We're going to select the path whose end is closest to the goal according to the heuristic function. So this is called best first search. Best first search selects a path on the frontier with a minimal h value. So before we did the minimum cost, least cost first, selected the element on the frontier with the minimum cost. Now we're going to select the element on the frontier with the smallest h value. So the implementation is the frontier is a priority queue ordered by h. Okay? Then now you know the algorithm. I can just... All right. So what happens in this graph? We're going from S to G. What happens? We're always selecting the node closest to the goal. The Euclidean distance, we're assuming our heuristic function is just distance. It ends up in the cycle. So if we do this, it ends up going just around these red nodes, because these red nodes are close to G. And it never checks the green nodes, because that green node up there is a long way from G. So it never finds this path G. So it turns out that best first search is sort of not a good idea. It seems like a good idea, but it actually doesn't work very well. We don't have time. We're running out of time here. Let's just go through this quickly. Does best first search guarantee to find the shortest path or the path of the fewest arcs? No. What happens on infinite graphs or on graphs with cycles, even if there's a solution? You're right, it can get stuck in them. What's the time complexity? As a function of the length of the path selected. Right, what would you guess? Well, but it's a function of the length of the path selected. So as the path goes on and on, it gets the path length. For the cycle, it goes on and on. All right, yeah. Oh. So the answer is it's exponential. As time, the space complexity is also exponential. The graph, the frontier can just keep growing, right? We can keep doubling the size of it all the time. We can keep increasing. Every time you go a step, we can start doubling things up. And it turns out it has all the worst properties of everything we've seen so far. But the goal, however, does affect the search. So we've at least got something. All right. So let's move on from that. So the one that we mainly want to talk about is A star search. It uses both the path cost and the heuristic values. So remember, cost of P is the cost of a path P. And H of P estimates the cost from the end of the path P to a goal. And we're going to let this F of P be the cost of P plus H of P. So we have the cost of the path from the start node. So if we look at this, we have a cost from the start node to P is the cost of P, the estimate of N from the goal, and that's all F of P. So it's an estimate of the cost from going from the start to the goal via the path you've already handled on there. Okay, does that make sense? So we're going to estimate not just the path from the start to the node, like we did in lowest cost first, nor just an estimate of from N to the goal, but we're going to add them together because that's the total path length. All right. So what happens in this graph? So remember what happened before with best first search, it got stuck into a loop. What happens in this graph? Does it get stuck in that loop? Why? Right. So when we're in this loop, the cost is going to keep increasing as we go down there, and eventually the cost of this node to the top left is going to be less than this. So the cost in that loop keeps going down. Okay, let's give some examples. I have to reload it. I shall load this one. Load this. Solve it. Oh, let's view. Let's get rid of all these things. And I'll show the. And whoops. All right. This is a graph like the ones that we did for the finding a path from UBC out to Stanley Park. And so let's look at what A star search does here. So it's going to start off with just UBC. It's going to expand, so we're going to start off at UBC. We're going to select it, it's the only one on there. We're going to add its two neighbours to the frontier, and we have a new frontier. What's it going to choose next? JB, Jericho Beach, I think it is. Right, so it's going to choose that. It has a H value of, the nodes, that number in the node is the heuristic value for Stanley Park at 0, for Jericho Beach it's 3, and the arc cost, the ones on the arc. So which one's it going to choose? Right, it's going to choose the Jericho Beach because it has an H. So the path cost is 3 plus 3 is 6. So it's going to choose the value of 6. Okay, so it's going to choose that. Then going to add its neighbours on. And now what's it going to choose? KD, right? 7 plus 3 is 10, and the other is 3 plus 6 is 9. So it looks as though this KD might be better. Then it's going to add its neighbours in. There's 3 things on the frontier. What's it? 7 plus, what's it going to choose? Oh, they're the same, aren't they? That's fine. It's going to choose one of them. It's not going to choose MP, right? It's going to choose this one. It's going to add its neighbours to the frontier. Now what's it going to choose? What's the value for Jericho Beach there? Okay, wait a minute. Running out of time here. What's it going to choose? It's going to choose, well, what's on the frontier now? There are a few paths on the frontier. It's got to KD to B, and from UBC to Jericho to Kitsilano Beach to downtown. Oh, let's do this. What are the paths it has here? It has UBC to KD to JB. What's the value for this? What's the F value for this? Well, this is. We have them both. What is it? No, it's 3 plus 4. What's the heuristic value for this? The one on the node. 3. And what's the answer? What's 3 plus 4 plus 3? Who can do arithmetic? 10. And it has UBC to JB to KB to Burnaby. What's that value? Well, it's 3 plus 4 plus 6 plus 8 plus 8 is what? 7. Who can add? 21? What else is on the frontier? Shall we start at the start? We'll do this properly next time. Right, there's UBC to Jericho Beach to KB to downtown. What's the value for this? 3, 4, 2, and 2 is 11. Is that right? Okay. So you're going to select one. It's going to select this one. It has 10. Because this is the path cost. So the path cost, this is called the cost, the path, plus the h of the last node equals the f of the path. Right, so you're doing the cost of the path plus this h of the last node is the f of the path. Yes? Otherwise, it ends up being, if this is 0, if we ignore this, it's the same as what algorithm? If we ignore this, what algorithm is it called? Right, this is lowest cost first if we ignore this. So if we ignore this, it's lowest cost first search. If we take this into account, all of a sudden we're going to head towards downtown and not head towards the airport. And if our goal was to head to the airport, see here we're going to ignore the airport. If the goal was to head toward the airport, we'd ignore downtown. Right, so we're going to look at the distance to the airport. All right. Let's stop here, have a look, and we'll go through it again next time.